Okay, remember what I said on the area notes, assuming, of course, you watched the area notes. Any triangle that you're trying to solve, let's say that I give you a triangle that looks like that, or I give you a triangle that looks like that, or something like that. Any triangle that you try to solve, you could simply redraw the triangle, take any one of them, and simply flip it around and twist it, and you could make any one of these sides a flat side so that you could technically declare it as the base of the triangle, which is going to make it easier to solve. And if you take any triangle that I give you and you redraw it on a graph paper, then you could also take that triangle and draw it so that one of the corners was at the origin, which also would make the rest of the triangle easier to solve. So that's essentially what I've done. Is here I've given you a triangle. It's just a random triangle, and I have twisted it and turned it and oriented it so that one of the sides is flat on the x-axis and one of the angles is at the origin. And then I named it. And once again, that was random. I could have decided that this right here might have been angle B instead, or angle C. I just went in order. I started here at the origin. I called that point A, and then I called this point B and called that point C. And once I had decided that, remember from geometry that if this is angle C, the side across from it has to be side C. So I can take any triangle that I want to solve and I can orient it so that it looks like this graph. So this is not something that you have to be given. You can take any triangle and draw it on graph paper and accomplish this. So what I've done is I have put angle A, or point A, at the point 0, 0. Since the side across from angle C is side C, so it's little c, and that C value would tell us how long this side of the triangle is, that means we also know the coordinates for B, because you notice that this graph wasn't scaled, so we don't really know that every grid line is 1. So however long C is, that tells me how far to the right that point is, and of course it's on the x-axis, so the y-coordinate is 0. So the coordinates of angle B are whatever the length of C is, and then a y-coordinate of 0. Okay, and then the side across from angle B is of course side B, and the side across from angle A is side A. And our goal would be to know the location of all of these angles, the lengths of all of the sides, and that would allow us to find the size of all of the angles as well. So we could do what we call solve the triangle. Solving the triangle means you want to know all 3 sides and all 3 angles. So you know everything there is to know about that triangle. So there are a couple of things we still don't know about our triangle. We know the location of A. We know the side C. We know the location of B that determines. We don't know the location of angle C, because once again, we don't know what the scale of this graph is. So what we do is we drop an altitude or a line down to the x-axis, just like we did on the area notes. So remember what that means that I'm about to do. Let me switch colors here. I'm about to try to do this. There's my altitude. Now, if I was doing the area notes, I would have said, oh, hey, this altitude tells me the height of my triangle. And it still does, but I'm not using the height to find the area anymore. I'm looking for the coordinates, the x and y coordinates of this point, so that I know where angle C is. And remember, just like all the other triangles we've constructed since we started trig, this right here. So once again, just like with the area notes, if this side right here is going to tell me what my x-coordinate is, because it tells me how far to the right of the origin I am, and this point right here would tell me what the y-coordinate of that point is, because it would tell me how far above the origin I am. Then what I've just constructed by dropping this altitude down is I've constructed a right triangle. So what we would do is we would do the same thing we did on our area notes. We would use this angle. This angle was part of the original triangle, and we would use this side. It's one of the sides of the original triangle, and we're going to use it to find this side and this side of the small inner right triangle that we've constructed. So let's say I was trying to solve for this x-coordinate right now. I would use the angle from my original triangle and this side, which is the hypotenuse of this little right triangle here. And I know that the cosine of angle A would be this adjacent side right here, would be the x side that I'm looking for, over this side right here, which is the hypotenuse for that little inner right triangle, which is B. And that means I could rearrange it to solve it. And so to solve for this x-coordinate right here, it would be B times the cosine of A. And so that gives me a formula that would solve for this x-coordinate right there. Okay, so what I'm going to do then is I'm going to, because my picture's getting too cluttered, instead of calling this side x, I'm going to call this side B cosine of A. Okay, and then the other thing that I need to solve for is I need to solve for this side right here, which is y. And I would do something very similar. It's just that using this angle, and I would use this side, and this time I'm going to be trying to solve for the side opposite from it. So this time I would know that the sine of angle A would be the opposite side, which is the y value I'm looking for, over B. And once again, I would rearrange it, and so the formula to find the y-coordinate of this point up here would be B times the sine of angle A. Okay, so what that means is I'm one step closer to having my triangle solved. The one thing we would have left to find would be this side over here. And that would be little side A, okay, because it's across from angle A, right? And we still have not figured out a way to find it, okay? But what we know is we know several things. Let me do some erasing first, okay? So what we would know is we've dropped this altitude down. We have figured out our x-coordinate with a formula. We have figured out our y-coordinate with a formula. So we would now theoretically know the location of all three angles. And we would be able, once we know the location of this, it would just be really easy to use the Pythagorean theorem to find this. And we would know this because it's right on the x-axis, and we can just measure the length of that. The only thing we still need to find is this. But when we dropped that altitude down and we made a right triangle out of the left side, it means we also made a right triangle out of the right side. And that right triangle, we would now know two of the three sides of. We would have y up here, and we have a formula to calculate y. We know the length of this side just because the total length of this is c, and this little section of it is x. And so the length of this would just be a matter of subtraction. We would just do c minus x, and we would know the length of that side. And that means to find the final piece of information about our triangle, we could use the Pythagorean theorem. Okay, now you're never going to have to prove this or derive this, but it's still, I think, very interesting and useful to know where it came from. And the law that we're deriving is the law of cosines, and it truly is just a slightly more challenging version of the Pythagorean theorem. Okay, so what I'm about to do is I'm about to do the Pythagorean theorem on this triangle over here on the right. And I'm going to do just a bunch of substitution and then a bunch of algebra. So the Pythagorean theorem, the way that you guys know it, would of course just say a squared plus b squared equals c squared, right? But we've renamed everything. We're trying to solve for a triangle. This is what the right side of that looks like. This is y, this is c minus x, and this is what we called side A of our large outer triangle. And so we're going to rename everything, and then we're going to do some algebra. So this is one of my legs right here, y, and it's going to get squared. This is the other one of my legs, and we find its length by doing c minus x, and that's the length of that leg, and it's going to get squared. And that's equal to our hypotenuse squared. And now comes the algebra. Okay, and so what I'm going to do is number one, I'm going to substitute. We have a formula from the upper half of these notes that said that our y value was b times the sine of a. We have a formula that says that x is b times the cosine of a. And so what we can do is we can substitute. So I'm going to replace y right here with b sine of a. That's the formula that would calculate what y is, and it's getting squared. Then I have my c, of course, minus, and then I'm going to replace this x with the formula that would calculate what x is, and that formula was b times cosine of a. And that whole thing is getting squared, and it's equal to a squared. So there's the substituting. Now comes the ugly algebra. Okay, and if the ugly algebra part is going to confuse you, then you can fast forward through it. Like I said, I just think it's cool to watch how all this simplifies down and becomes something that will look familiar. Okay, so I'm going to go ahead and I'm going to do the algebra to actually show you where the law of cosines came from. So when I square this, it just becomes b squared times sine squared of a plus, when I square all of this, I have to FOIL, because this is c minus something. It's a binomial, and so I'm going to have to FOIL it out. And so when I do that, I get c squared minus 2bc cosine of a plus b squared cosine squared of a. It's a huge mess. Okay, and you can always jump off to the side or pause the video and prove that to yourself. Multiply, I don't have much room, but multiply c minus b cosine of a times c minus b cosine of a. That's what it means to square it, is multiply it by itself. And show yourself that you get the same thing. Okay, but now watch what, that's cool, it's about to happen. Okay, so I'm just going to do a little bit of rearranging. I've got my b squared sine squared of a, and I'm going to take this part right here and I'm going to move it up with it, because I can add in any order. Okay, and then I have this part right here, the plus c squared, and then I have this part right here, the minus 2bc cosine of a. Okay, now if I look at these two terms right here, they both have a b squared in them. So I can factor it out, b squared, and when I factor it out, it leaves a sine squared of a plus cosine squared of a. And then the rest of it, just, I continue to rewrite it, it just tags along for the ride. And believe it or not, I'm basically done, because sine squared plus cosine squared is just 1. So what we have is, this whole thing is just b squared, because it's times all of this, which is just 1, it just goes away. Then we have the plus c squared right there. And then we have the minus 2bc cosine of a, and it's equal to a squared. Okay, now it looks like this huge mess, but I want to point something out. So I'm actually going to do a little erasing because I can't cover up with my finger on a video notes. Do a little bit of erasing. Erase this part right here. And what does it look an awful lot like? Hopefully you're thinking it looks a lot like the Pythagorean theorem. And that's actually because it is. It is the Pythagorean theorem. It's just the Pythagorean theorem that works inside of all triangles, not just right triangles. And that's all that the law of cosines is. Okay, and the reason that it is just the Pythagorean theorem, but for all triangles, is, and it even works inside right triangles, is because let's say that A was a 90-degree angle. If A was a 90-degree angle, then that would make little a, the side across from it, the hypotenuse of the triangle, because it would be across from the 90. And so then if I tried to use this formula for it, what it would say is it would say a squared is equal to b squared plus c squared minus 2bc cosine of 90 degrees. And what is cosine of 90 degrees? Cosine of 90 degrees is 0. And so this whole part of the formula would just vanish. And that's what I think is so cool, is that this actually is the Pythagorean theorem. It's just that when the angle right here is 90 degrees, this whole big messy part at the end of it disappears. And it just becomes the version that you guys know and have known forever. Okay? Now the reason that there's 2 other lines right here is because, once again, the naming of the sides was random. Okay, I could have made it triangle CBA or CAB. I mean, I could have put it in any order. So once again, there's a pattern to it. When you're looking for side A, then what you need is you need side B to use here, and you need side C to use here, and you need angle A. So if I was looking for side B, then I would need to know what side A is. I would need to know what side C is, so that I could do a squared plus c squared minus 2ac. And then if I'm looking for side B, the angle I would need to know would be angle B. And so then the third version says if I'm looking for side C, so c squared equals, that means I would need to know side A and side B. So I could do a squared plus b squared minus 2ab. And then if I'm looking for side C, the angle I would need is angle C. So this is how we use this formula, okay? Because it looks just like a much messier version of a Pythagorean theorem, okay? So what we do is, a lot of it is just plugging and chugging, but what I would strongly recommend you do is draw pictures. So this example says 2 sides of a triangle are 3 centimeters and 7 centimeters, and the angle in between them is 130. So I'm just going to eyeball it, okay? I'm going to draw a short side. I'm going to draw a longer side. And I'm going to put what looks like about 130 degrees between them. Okay? So this is my 3. This is my 7. This is right there, the 130 degrees in between them. Okay? And I can name them, anything I want to name them. We try to stick with A, B, and C a lot because most of our formulas are A's, B's, and C's. So I usually let the classes just choose, but since I'm doing this for myself, I'm just going to choose. Let's say that this is angle A, so that means that this is side A. Let's say that this is angle B, so this is side B. And let's say that this is angle C, which means this is side C. And that's what I'm being asked to find, is that third side, side C. So I write down the law of cosines, so c squared equals Starts out looking like the Pythagorean theorem, a squared plus b squared. But then there's this new part, 2ab, and then cosine of angle C. That's what the law of cosines says. And then I literally just plug numbers in. So C squared equals A is 3, B is 7, minus 2 times 3 times 7 times cosine of 130 degrees. And it's going to require a calculator. And the nice thing about our calculators is that you can literally type this entire thing in exactly as you see it written here. It'll take care of the PEMDAS exactly the way that it is. And so you just type it in, and of course you make sure you're in degree mode, because our angle is 130 degrees. And when you type all that in, you end up with C squared being equal to 84.99707.961. And then you take the square root of it. And once again, your calculator will recall all of those digits and take the square root of it, and you get 9.219 centimeters. Now, one of the things we're going to rely on very heavily in this unit is the geometry of the situation. If you look at the size of this side, that makes side C the longest one of the triangle, which makes sense because it's across from 130 degrees, which would obviously have to be the biggest angle in the triangle. Okay. One thing that geometry also talks about or alludes to is that we can rearrange the law of cosines to use it in another direction. Okay, because we want to know, hey, if this is the longest side across from the largest angle, then, you know, what if I knew the sides instead? And so what we're going to do real quick is we're going to rearrange this law of cosine, because there are times when we want to use it, b squared minus 2ab cosine C. There are times we want to use it to find the angle instead of the side. Okay, so what I'm going to do is I'm going to take the C squared and I'm going to subtract it to move it over here, and I'm going to take this minus 2ab cosine C and add it to move it over here. And so what that would give me is, I don't have enough room, I'm going to do it down here. It would give me 2ab cosine of C on this side, and it would be positive. And then over here it would give me a squared plus b squared minus c squared. And so then the only thing I would need to do to allow me to solve for an angle is I would need to divide both sides by 2ab. Let me go ahead and just scratch it out. Because then what that has given me is it has told me that the cosine of angle C is equal to a squared plus b squared minus c squared over 2ab. And it's a rearranged version of the law of cosines that helps me solve for angles instead of sides. And once again, there's a pattern to it. What it's saying is that if you want to find angle C, that the only place you're going to use side C is at the tail end of the numerator as the only part of the equation that gets subtracted. Everywhere else you just need side A and side B. Now once again, what that means is that there's other versions of it. Let's say that I had named my triangle differently, or let's say that I was solving for one of the other angles. If I want to solve for angle B, so cosine of B, that means the only place in the whole identity where I use side B is at the tail end of the numerator as the subtraction part. Everywhere else I need side A and side C. So this would be a squared plus c squared, and this would be 2ac. And then the last version of it would be if I was using it to find angle A. The only place I would use side A is, once again, at the tail end of the numerator as the subtraction part. Everywhere else I would use side B and side C. Okay, and so we can use that in our rearranged version kind of problem. So the final example, the lengths of the sides of a triangle are 5, 10, and 12. Solve the triangle. So I'm going to draw a random triangle. I'm just going to make one side short, one side long, and of course one side even longer. Okay, so let's say that I say this is the 5, this side looks like it might be the 10, and this side is the 12. Okay, and I'm going to name them randomly. So let's say I call this side A, so that makes this angle A. Let's say that I call this side B, which makes this angle B, and that would, of course, would make this C and C. Okay, and it says solve the triangle, so we want to find all three angles. There will be other times where we just ask you to find one specific. If I said find the largest angle, then we know that would be angle C because it's across from the longest side. Okay, but this one we just want to find them all. So typically what I do is I just go alphabetically. So if this is side A, I'm going to find angle A first. So I would do cosine of A is equal to, and then once again, if I'm looking for angle A, the only place that side A gets used is at the end of the numerator as the subtraction step, so minus 5 squared. Everywhere else, I use the 10 and the 12. So I would have 10 squared plus 12 squared, and I would have 2 times 10 times 12. Now you really want to do these as individual steps in your calculator. So you want to do the whole numerator, do 10 squared plus 12 squared minus 5 squared, and you would get 219. And then do 2 times 10 times 12, and you would get 240. And then you could do the inverse cosine step in your calculator. Inverse cosine, 219 over 240, and you would get 24.1 degrees. And that's it. That's your answer for angle A. And the nice thing about using the law of cosines to find your angle means you only ever get one answer. So cosine for an angle only has one answer. Remember the last problem we did on the area notes, anytime we use sine to find an angle, we have two potential answers. And that's not the situation here. Okay? So if I'm solving my triangle, I need to find both of the other angles as well. So I would suggest you pause the video and try to find, just go alphabetically, let's do B. Okay? Okay, so hopefully you paused it and you tried to set up B. So I'm going to do cosine of B is equal to, if I'm looking for angle B, the only place side B gets used is as the subtraction at the end of the numerator. So the 5 and the 12 are going to get used everywhere else. So I'm going to have 5 squared plus 12 squared, and 2 times 5 times 12. So that means cosine of B is going to be, if we did the numerator, 5 squared plus 12 squared minus 10 squared is 69. And then 2 times 5 times 12 is 120. And so if I did inverse cosine of that, 69 over 120, that means angle B is going to be 54.9 degrees. And that's all the trig I have to use, because I know there's 180 degrees inside of every triangle. I know angle A is 24.1 degrees. I know angle B is 54.9 degrees. And so that means angle C, when I subtract, is going to be flat out 101 degrees, which once again makes sense. Angle C is definitely the biggest angle, and it's across from the longest side. Angle A is the smallest angle, and it's across from the smallest side. So the geometry of the situation makes sense. And my triangle is now solved. So sorry for the longer notes. This is a difficult concept. It's the hardest one of this unit. But we're just going to take our time and practice using these formulas in the coming days.